You know when you see one of those long, kinda crazy-looking polynomial equations, the ones with all the x's and squares and cubes, it's easy to just feel overwhelmed, right? But here's the thing. What if I told you that they're not just a random jumble of symbols? There's actually a hidden logic, a secret code baked right into them. And once you see it, you can unlock their secrets without all the hard work.
All right, let's jump right in. Look at this thing, a big old quartic equation. See all those letters out front? The A, B, C, D, and E? We call them coefficients. But you know what? Don't think of them as just numbers. Think of them more like clues. Yeah, like clues in a detective story. They're trying to tell us something really important about the final answer to this puzzle. The real question is, what are they saying?
So here's the main idea we're going to unpack today. It's actually pretty wild. The numbers that make up the equation, those coefficients, they can tell you a ton about the solutions, the actual values of x that make it all true. We call those solutions roots, by the way. And the cool part? They tell you this before you even try to solve for them.
And listen, this isn't some weird math hack or a gimmick. It's a really deep, fundamental truth that mathematicians figured out over centuries. These connections between the numbers in the equation and its answers, they're like a blueprint, a powerful shortcut that gives you a peek into how the equation is going to behave just by looking at it.
Okay, so where do we start cracking this code? Let's begin with the one we all know and maybe love, the good old quadratic equation.
And here it is, in its familiar form. This really lays out our whole mission, doesn't it? On one hand, you've got the stuff you know, the coefficients A, B, and C. And on the other, you have the mystery you're trying to solve, the roots, which we'll call alpha and beta. Our job? Find the hidden bridge that connects them.
Boom! Here's our first secret key. It's so simple, it's brilliant. If you want to know the sum of the two solutions, you don't have to find them first. Just grab the B coefficient, slap a minus sign on it, and divide by A. That's it! You instantly know what alpha plus beta is.
And the second key is just as elegant. What about their product? What do you get when you multiply the two roots together? Again, just look at the equation. It's that last number, C, divided by the first one, A. That's it. It's that simple.
And right there, that's our first big aha moment. Think about it. We didn't have to touch that big, messy quadratic formula. We didn't solve for x at all. But we've just pulled out two super important facts about the solutions just by looking. This is a huge first step in cracking the code.
Okay, so we've got the quadratic figured out. But here's the big question. Was that just a one-off trick, a special case? Or are we on to something much bigger here? Let's push this a little further and see what happens.
Oh, wow. Okay, check this out. This table just lays it all out perfectly. Look, the sum of the roots, taken one at a time, it's always negative b over a. Doesn't matter if it's a quadratic, a cubic, a quartic, always. Then you look at the next level, the sum of the roots taken in pairs, it's always positive c over a. And the product of all the roots, see how the signs just flip-flop, plus, minus, plus? It's this incredible, consistent pattern. It's not random at all.
And I really want to drive this home. This is not a coincidence. This isn't just some neat party trick. This is a deep, fundamental property of how these equations are built. It's like we're seeing the architectural plans of algebra itself. It's beautiful, right?
So, we can find the sum and product of the roots. That's awesome. But what if we want to know something different? What if we want to know what kind of numbers the solutions are? Are they real? Are they imaginary? For that, we need to pull out the master key. It's called the discriminant.
You probably remember the whole quadratic formula from school, right? Well, forget most of it for a second, and just focus on the part that's tucked away under the square root sign. That little expression, b squared minus 4ac, that is everything. That is the discriminant. That's our master key.
And here's why it's a master key. Just by figuring out that one number, you can basically predict the future of the equation. If that number turns out to be positive, you know for a fact you're going to get two different real solutions. If it's exactly 0, you're getting one single repeated root. And if it's negative, well, that's when you know you're heading into the world of complex numbers. You're going to get two complex solutions. And you know all this without even solving the equation.
So that's its superpower, right? It doesn't tell you what the roots are, it tells you what kind of roots they are. It's like a fortune teller for equations, letting us know if the answers are going to be nice and simple or something a little more complex.
Okay, theory is great, but let's get to the payoff. What's the point of having all these secret codes and master keys? Let's put them to work on a problem that, at first glance, looks, well, pretty much impossible.
So here's the challenge.
How on earth can you prove that this big expression is always greater than or equal to 0 for any real numbers you plug in for x, y, and z? I mean, you can't test them all, right? That's infinite. You'd be here forever. We can't use brute force. We need something smarter. We need that master key.
Okay, here it is. This is the inequality we have to prove. And yeah, it looks like a total mess. But what if we look at it through a different lens? What if we stop seeing it as a 3-variable mess and start seeing it as a simple quadratic, just in terms of x? Suddenly, things get a lot clearer. So, here's the 3-step takedown. First, we just rearrange everything so it looks like a normal quadratic with x as our variable. Second, we whip out our master key and calculate the discriminant of that quadratic. Now, after a little bit of algebraic cleanup, the discriminant simplifies to something amazing. -3 times the quantity y minus z squared. Now think about that. A number squared is always positive or 0. So if you multiply it by -3, the discriminant has to be negative or 0. It can never be positive. And what do we know about a quadratic whose leading term is positive and whose discriminant is never positive? We know its graph is a parabola that opens up and either just touches the x-axis or floats completely above it. It can never ever go below 0.
And that's it. Proof complete. With one incredibly clever move using the discriminant, we've proven, beyond a shadow of a doubt, that this expression can never be negative. It's like a magic trick, but it's just pure, beautiful logic. So, what's the moral of the story? It's pretty much what Hofu Him says in the source material we're looking at. The discriminant is an unbelievably useful tool. Understanding these hidden codes inside equations, these relationships, the power of the discriminant, it really is like having an algebraic superpower. It lets you tackle these huge, complex ideas with pure elegance and confidence. And that really leaves you with a final, pretty mind-bending thought, doesn't it? If there's this deep, beautiful, hidden connection between the numbers in an equation and the answers to it, what other secret relationships, what other hidden codes are just sitting there, waiting to be decoded in the rest of mathematics?